Good morning. Today we are going to talk about cryptographic algorithms and their various implementation and mitigation techniques. So, I pretty much tried to not get into mathematics, just stay in the very higher level of abstraction to cater two types of people. If you are trying to implement, where would you start? And if you already have an implementation working in industry, you want to integrate into their system, where would you start? So, it is from both perspective, developer and as well as designer. Once we talk about these algorithms or at least give you an overview, your objective would be two things: to understand what does these algorithms actually achieve, how do they achieve it, why there are so many algorithms, which one is better than whom in terms of the security strength and hardware overhead. If I have an objective function, if I am trying to design a system, which one do I implement and why, and also some idea about what are their security strengths, what kind of mitigations can we do, all that stuff. So, it is a laundry list of items. Initially it may seem scary to you, but as I said, I am going to go through very simple thoughts, very high level idea of what they do. So, before we start, let us start with the usage model. On your laptop, you are trying to do a banking transaction. You opened an HTTPS, or you have on your phone, you have the app, secure app, and when you basically try to talk to your bank or connect to the bank server, secure server, it is basically uses transport layer security. In fact, most of the cryptographic algorithm that I am going to talk about is basically what this today's transport layer security uses, and I am just listing them. Right now it may seem like too much scary, but eventually I will zoom into each of them. And so, whether it is an encryption algorithm, what is the key size, what is the mode, what is the hashing or authentication mechanism. So, that is basically what I am going to talk about. So, you get an idea. That is the first thing you will understand, what is getting used and what they are actually at the right at the bottom bits and pieces. And then most secure or root of trust is actually the processor in your design. Processor, in fact, the processor which uses some secure socket layer, one of the implementation it runs, you will get an idea of that too. But more importantly, even the processor itself is not secure, or the whole environment, to make sure there is something called security engine. So, I am going to talk about that security engine. Most commercial products that you buy, whether your phone, whether laptop, whether TV, in addition to all the chipsets you hear about, you mostly do not hear about this node called security engine. So, I am going to talk about that security engine, but of course, security engine by itself is not useful. It takes help from all these cryptographic modules. So, that is basically the power and how that security engine works. So, and that is basically I am going to zoom in. That security engine may include processor may be outside, or the security engine may have a processor on its own, which is not the general purpose processor that is used for doing your HTTPS and secure socket layer and all that. It may have all the stuff, but today I am going to zoom into the cryptographic components and how do they talk. Is it inside the security engine, is it outside, how do they help each other. So, today I am going to basically zoom into this component. So, anybody has any question on the context? You are trying to do any secure communication through VPN, SSH, SFTP, HTTPS, anything you do, the root of trust these days in the system on chip domain is controlled by something called security engine. Now, you might say, well, wait a minute, did not we talk before about trusted execution environment, security enclave and all that stuff? How does that relate to it? It relates in the sense this security engine is giving you this same level of opportunity. Your trusted execution environment could be implemented on it, it could be orthogonal to it. Now, before I go further, we want to again reset our context, what we are trying to achieve and why, and this all boils down to same thing, a notion of a sender and a receiver and in cryptographic community they are known as Alice and Bob, and it is all about passing a message, and assumption is this area is trustworthy, this area is trustworthy, and as you go along we will also break that notion, and communication is something potentially untrusted. So, therefore, when I am sending the message, my expectation are at least these three things. Authentication, when a message comes from S and the recipient is looking at it, it should be from S, it should not be from anybody pretending as S. So, that is the authentication. And then privacy, when S and R talking, nobody should be listening to this conversation and understanding. So, this should not be allowed. That is basically the privacy issue, and the integrity issue is, if I am not able to hear, can I actually alter whatever the message is, can I alter the message before it goes to R prime, that is the integrity issue. And different cryptographic components are designed to address these things, and today we are going to zoom in. For example, data integrity could be SHA, it could be parity code, it could be checksum MD5. Actually, the initial version of SHA was built on top of MD5, and then eventually that got broken. Now, the SHA2, essentially SHA2 is used today. SHA2 and SHA3, those are used in today's protocol. The TLS uses SHA2, and that is what I am going to zoom in. And then for authentication, you basically want somebody to sign, like the way people sign the check, somebody's signature. So, this is basically authentication mechanism, and for privacy you need some form of encryption. It could be AES, RSA, ECIS, and we will zoom into some of those components, but I wanted to put them in the perspective, so that when I talk about each of these module, it should not appear to you some bunch of random stuff. They have their clear objective, but some point later it may seem blur, because many of the encryption techniques actually is authenticated encryption. In fact, RSA, although it is an encryption technique, you can also use for some form of authentication and signature mechanism. So, there are bound, in fact, this ECDSA and ECIS comes from elliptic curve cryptography. One is primarily for encryption, another is primarily for authentication, but whichever it is, and even things get even worse, many of these techniques like ECDSA actually makes use of SHA as in the back end hashing mechanism. So, what I am going to do after this context is clear, I am going to zoom into each of them and very conceptually look at what they try to achieve, what are the challenges, and how can we solve some of the challenges, and that would also tell you what are the vulnerabilities, because all the guarantees that are given to you are by these cryptographic modules, and if they fail, then everything you build on top of it, which is security engine, on top of it you have transport layer security, everything fails. And that is why this is known as hardware root of trust, and that root of trust relies on the guarantees of this module at the absolute bottom layer. Always we had this feeling, or unless you learn cryptography, you will always have the feeling the hardware root of trust is basically based on CPU, which is partially true, because as I go along I will talk about RISC-V based cryptographic extensions, which is a software kind of pseudo software based implementation of security. So, this is true, you can run each of these modules in software, in fact in TLS that is what it is, or you can speed them up as a hardware implementation, and that is when you hear cryptographic accelerator. It is actually not an acceleration that we discussed in this class, not GPU based, not TPU based, not FPGA based, it only means same cryptographic module implemented as a hardware. Any question? Cryptographic accelerator is nothing but hardware implementation of all the algorithms we talk about, and if people do not talk about acceleration, then it basically means the software functions you are calling, or somebody is calling. Who is that somebody? CPU is somebody. So, therefore, calling CPU as root of trust is actually not a flawed assumption. but for majority of the cases CPU does not participate any of these activities. Directly security engine with its own controller, call this, let us say it has its own cryptographic modules, AES module, and I will show you exact framework of that. Any questions on this? Now, authentication, you know what you are trying to achieve, that is what you will achieve using some form of PCDSA, and little bit of introduction of encryption before we zoom into how AES achieves it, how RSA does it, because our objective is, we believe the sender, this is a plain text message, this part is secure. We believe receiver, again plain text message, this is secure, but the message need to be encrypted, this is ciphertext. So, basically one of the mechanism is you encrypt it. So, encryption, you give the plain text, whatever message you want to, if you do not like the word P, change it to the message M, and then you need a key, and then it produces the ciphertext. Now, for decryption, you give the ciphertext and you get back your original message. That is the key idea. Now, we talked about earlier, there are two types of, and we will have examples of both today. Symmetric crypto systems, when the keys are exactly same key it operates with, and then we will have asymmetric crypto systems where keys are different, and these also have different variations, but typically this one is easier except the key distribution problem, because you have same key. This one is easier in the sense when a sender and receiver is there, then when sender sends to the receiver, it basically encrypts with the public key of the receiver's public key. And the way algorithm is designed, that when the receiver receives it, this ciphertext, it basically uses its own private key, okay, public, let us call it PL. It uses its it decrypts this particular message ciphertext using its own private key, let us call it PR, and private key nobody knows. Now, the beauty is sender is not sending to just one recipient, sender is sending to maybe multiple of people, and everybody has their private key, sender is not aware of it, but sender is aware of everybody's public key, that is why the name public key, and same argument applies, the receiver one also knows the public key of sender. So, during encryption process, you basically use the public key of whom you are sending the message and use that public key to encrypt, and the way algorithm is, decryption time everybody uses their private key to open it, and key sharing problem is solved. Public key is a known thing, you can just put it anywhere and everybody knows. Now, during authentication process, it is actually inverse of the problem. When you are trying to do authentication or sign, you sign using your private key. The way algorithm works, everybody when they receive, they be able to figure it out using your public key. So, R would be able to figure out using your public key. So, that is basically the swap of the story. But either way, each of these has pros and cons, and sometimes even if key is not equal, many algorithms, as you will see, one key can be derived from the other, and I know that has some technical flaw, but you would see soon. Any question on the basic idea of why we are doing encryption? Because we do not rely on this communication, we believe somebody will steal it, we believe the privacy is in danger, that is why you want to encrypt, nobody can listen. So, threat model is this part or this part of the communication is not trustworthy. So, this part is not trustworthy. So, that is the threat model. In that threat model, we are doing encryption to make it secure, and then encryption we have two choices. Do we have same key for everybody? Encryption, decryption, sign, verify, everything is same, and here you have different, and signing verification process the key usage, and encryption process key usage is exactly opposite. These are very basic concepts. Now, let us get into the first one, AES. AES is a symmetric key encryption algorithm, later we will come to asymmetric key. like elliptic curve cryptography is a asymmetric key, public and private. It is a symmetric key algorithm, and Dr. Korfa talks in detail. So, I will give a perspective from a different way about this algorithm. So, this one is adopted by National Institute of Standards and Technology in 2001. It operates on 120 bit block sizes. If you have an email you want to send, whatever the text it is, it would be broken into 128 bits, and then you will be encrypting those 120 bits, and because you are breaking it 120, this is also known as a classical block cipher. You are operating block by block. So, from a cryptographic point of view, block ciphers are not really very strong encryption algorithm. That is why DES or the predecessor of AES, those were broken in no time, and that is why nobody uses them. So, AES is still strong, and in fact, AES or with certain key sizes, AES 256 is exactly what is used in transport layer security, that the one that is used in your banking transaction. So, this particular one is used today. Now, from a layman's perspective, if you want to break this one, of course, it is lot more complicated than that. In a brute force, how many try do we have to do?
2^128.
How come? How did you get the magic number 128? This one, just the one I circled. I am trying to ask you, what is the brute force? How many try I have to do to break? So, what am I trying to break? I got a cipher text. I want to figure out what is the original message. How many times I have to try?
Okay, from a layman's perspective, I think there are 256 bits key. Okay, so in according to brute force, and if we use Grover's algorithm in our classical computer.
Okay, that is the answer, 2 to the power 256, because in any algorithm in security domain, assumption is you know everything except the key. Only thing you do not know is the key, and it has 256 bits. And so, then if you try all 2 to the power 56 combinations, then one of them has to be the key, there is no other way. So, this is the brute force, and if you look at this number, it is not doable in any meaningful time. So, therefore, but when if you recall the way Dr. Korfa talked about side channel attack, you can use some other mechanism where you do not need that much of time or resources, you utilize some other feature. I will talk about some of those features, then I talk about some of the mitigations. Any questions on this one, that when you look at any algorithm, if somebody says what is the strength, without getting into the details, no other information available, then the strength is 2 to the power of the key size, because key is the only thing not known to you, at least for AES that is true. Once we go along, there will be little deviations. Now, in addition to supporting different key sizes, AES also supports different mode. I will zoom into little bit of that. So, one is counter mode, and which is simply it is the easiest one. Then the Galois counter mode, and finally, the it is a big name XEX tweakable block cipher with ciphertext stealing. XEX stands for XOR encrypt XOR, XOR encrypt XOR. But whatever the big name is, AES XTS, I do not know, a lot of people use that one. Most people rely on the transport layer security uses AES GCM. Any question on this algorithm before we go in? And as you see in the picture, it is kind of you have lot of data, you are kind of shifting bunch of row, mixing some stuff, adding round key, you are basically making it complicated for somebody to just reverse those processes or figure that out. And many of those are based on the key, that is why unless you know the key, you will not be able to do it. Any questions on this basic idea? And one more thing I wanted to highlight. So, the idea is not, so the complexity of these, although I lament I am simplified this, but actually each of them are lot more complicated, because if you look at even the number of rounds is different for the different key sizes. So, it is not like it is exactly same thing. So, for example, what would have been exactly same if message is coming in and you are doing XOR with the key, and if the key size could be 128, it could be 190, it could be 192, or it could be 256, then it would be simple this one. But as you realize, its algorithm is actually different, the complexity is actually lot more different. So, now let me kind of get a little bit of perspective what AES trying to do, or what is this picture trying to do, this particular picture. And I am not going to get into any complexity analysis here, but basically it has a initial round, then multiple round and the final round. Final in initial round is just a round key and all that stuff, instead of going through boring stuff. Basically the subcomponents of each of those is basically some kind of sub bytes. Sub bytes is basically you are moving a specific location value from one table to another table. It could be you are shifting some rows. So, these numbers are getting shifted, this value comes to the left and so on and so forth, you are shifting them, or you are mixing some columns with other columns, or you are adding the rounding key and all that stuff that happens. And if you recall how Dr. Karpa talked about it, during these steps there are methods in the madness. By observing what computations are happening in S box, or what kind of round, what kind of pattern you are looking in your digital signature, you could try to figure out based on elimination or small brute force, was this location 0, was this location 1 and stuff like that. You can go from top down, bottom up, you are basically breaking down these sub problems or sub function and trying to figure out, and then you slowly percolate up or percolate down until you find the key. That is basically your objective. So, here is if you are going to implement, now this is, so if you go to open source, try to look for any cryptographic ones, first thing you are going to find is AES. Of course, you will find DES and the other ones nobody uses, you will find AES. You are not going to find, you are going to find AES, at least the encryption algorithm, decryption you may not find, and elliptic curve you are not going to find, and many others I am talking about you won't find, that is one thing. Second thing is, unlike this bus PCI and all these bus configuration which is standardized, for some unknown reason these are not standardized. Every company, and I will explain why that is the case, every company whenever they sell a security engine solution, they have their own kind of boundaries. So, I will show you at least two scenarios, so that you kind of appreciate why people do that. So, but when you are implementing, this is could be one possible implementation, clock, reset and start. So, start is important, because recall this is going to be part of, let me do little bit of security engine. So, security engine is again a piece of hardware that is going to sit somewhere on a bus, and that bus has to be not the bus where everybody else is sitting. This is one of the reliable, it could be AMBA AXB, it is typically not PCI, but this could be a PCI bus. On that bus, this cryptographic module would be hanging from there, AES would be hanging from there, AES counter mode. So, therefore, it is important for security engine, if it wants to encrypt a message and processor sends that request, by the way, that could be through another PCI bus. There are variations of PCI. So, this is where security engine is sitting, this is where CPU is sitting, and it send a request, and why processor is sending that request, because in your original program you have that encryption call, right. Who made that encryption call? In transport layer security, that application has that encryption of your ID, social security number, whatever it is, that came as a request as an instruction here. That instruction got request as a translation to security engine. Security engine in turn send that request. So, that think about your Aadhaar card ID or PAN number, whatever is secure, that is basically flying through, that is flying through from the original application of transport layer security to the CPU, to the security engine and to the AES, and then result would go back exactly the same way. Now, that is why this start is important, because hardware design by design they are always working, they are always computing something. That is why start and done, these two are important, and no spec will tell you this. You go to any documentation, they will not, but this is important, because when would security engine read the value and forward it to the CPU. Now, you could have done this through some synchronous mechanism, if you know it takes 32 clock cycle. Later I will explain you why that can't be done, or it is harder when many people are hanging. As I go along, you will realize slowly. I will build exactly on top of this how. So, some of these actually I will not take the name which company. So, some of the big semiconductor design automation companies like Synopsys, Cadence, Mentor Graphics, which is part of Siemens, when they sell the solutions, in their internal documentation they will provide exact details what they are supporting. So, that if you planning to add one more module, you are aware of what is there and what would be a problem. Go ahead please.
So one query is like in this diagram like you have shown with the PCI bus we have a connected AES module. So is that a hardware implementation such as an ASIC or something?
This is hardware implementation, very interesting question. This is hardware implementation. Software counterpart would be CPU itself is running, you do not need any more of any of this stuff. In fact, many times many companies when they sell security engine and nobody want to take a risk of trusted execution environment protecting you, they actually rely on the processor inside the security engine, and that processor will run that function, and that memory is sitting somewhere here. That security engine memory which will have your software binary for AES. So, this is a processor coprocessor model. In this example, you raise a very interesting question. In this example, CPU does not know how to handle any encryption decryption function. Anytime that instruction comes in, it forwards it to security engine. Whether security engine does through a hardware accelerator or through a software function call, it does not matter. Eventually, it will get the result. And so, in a hardware module, even software module, same thing you can do. Start and done is important. Now, clock and reset I do not need to mention those. Mode is of course important, that is the counter mode, which is in this particular example it would be set to counter. And then cipher key, this is basically this cipher key and this cipher key is same, and block in, this block in and this block in is the same. You might see why is it coming twice, you will see when Galois mode. It is once used for authentication, Galois authentication, once used for encryption. Nonetheless, so this is basically the one only thing. So, counter range, because it is a counter mode, initially it is 0, you can put it any value, does not matter, but what is important, this one is important. Anybody knows what is this nonsense? Nonce is a random number with a unique property. What is that property? Never used it again. So, I will talk about, when I talk about random number generator, I will talk about random number is actually not random. So, that is why there is a distinction between true random number generator and pseudo random generator. But nonce basically property, if you reuse it for any reason, even if random number, then replay attack will be able to break it. Any questions on this basic idea of? So, AES encryption, what it does, I briefly talked about this sub bytes and round keys. So, I am not going to get into this, but from a designer perspective you have to pay attention to these issues. You cannot just say, oh, I have a wonderful AES implementation, I ran it, but how come you are able to break? Because you gave a nonce that has got repeated more than once. You did not guarantee that, you did not check that. That is something, a property you want to check. Same thing for other stuff, counter, block in, and you probably did not start right, you took the value before the done is true, and all of those issues. Now, one simple thing I want to ask you is that cryptographic algorithms are mathematically secure, then how come people are able to break it? I want to hear your thoughts on this. All the mathematical algorithms, including the pathetic ones like DES that was broken long time ago, they are mathematically secure, guaranteed to be not broken by people unless you try the 2 to the power 256, which is like lifetime of the universe. Why is it we always talk about breaking things like AES 128, I do not think anybody uses anymore. How come? 2 to the power 120 is still a large number. Yes, please.
Because mathematically we are generally checking But like Professor Karfa told us that there are other methods such as the side channel method of cracking the AES.
Let us say side channel method is not possible, let us say Paul Cocker did not invent it, then do you believe it is mathematically secure, or do you believe it is secure? Yes.
Maybe with the help of quantum computer.
Quantum computer did not come into existence, do you still believe it is secure? You are on the right track. When mathematically somebody guarantees something, those variables are unbounded, but when you implement it, depending on the machine you are implementing, you are cutting many corners. When you say somebody integer, you are suddenly saying 32 bit, but the mathematician who guaranteed it and proved it, that did not have a bound of 32 or 64 or 128. So, basically those, the way you write if statement, everything has its own issues, and that creates all these covert channels and side channel vulnerabilities. Whether side channel was invented or not, it basically full of vulnerabilities, it is just waiting for somebody to exploit it.
But if somebody write the code in Python, Python do not have that. So, no means
Python, everybody has issues. Python is little stronger type than C program, but every language has same issues.
But they do not have actually this 32 bit.
Right, but when you are running that Python on a specific computer, it forces you to that machine's register size 32 or 64. So, that is basically, so I just wanted to distinguish you something mathematically correct, there is no flaw, something breakable, that is also no flaw. The fallacy connection is when you implement, you basically tie it to the implementation details, that basically mathematicians did not take into account, and from an attacker perspective, that is what people look at. Now that it is 32, 64 going through processor to cache, this mathematical guarantee does not look into the cache misses, cache timing, it is completely oblivious of it. When you introduce those features, that makes it vulnerable. So, now that you are done with the counter, so how would you use it? So, whether software, hardware, it is a similar pattern. So, you have to provide this in certain way, whether it is the key size and the key, the mode as counter, non certain value, and what is the counter. If it is a counter mode, you have to give counter start name, and if you are doing a software call, you have to create a file wherever you are putting this, or whatever way it is, you pass those parameter, and this one is simply calling the function from libgcrypt. So, software implementations of all of this is available from libgcrypt, libgcrypt library, and it is quite possible Python has already connected to, it is already connected to Python library. If not, just use libgcrypt.h and all software functions you will be able to call. Compilation would be little issue, because this thing has known issues with compilation error unless you do exact right versions. Nonetheless, when you test them, you basically run with different plain text, ciphertext. Can anybody tell me how do I test a AES module? Let us say software implementation is given, how do I test it? What would be the test case? Remember we talked about verification, how do you verify the functionality? Let us forget about vulnerability, which we will talk in a moment. How do you verify AES module? You know it does encryption. What you do not know, if you encrypt the encrypted message, how that would look like, because 2, when you add 2 plus 3, you expect 5, because you know what 2 plus 3 would be, that is your golden model. There is no golden model. If I give you only one model, just one AES module, how would you test it? I saw a hand, go ahead.
Sir, we can do one thing, we can encrypt first, and when we got the ciphertext, we can decrypt it.
Thank you.
Get the same plain.
Thank you. So, that is why when things looks really, oh my god, how do I do it, it is not 2 plus 3. In elliptic curve cryptography, this will become really complicated, but you simply any message you give, whatever message, this case I gave some message, meet me at the office, any message you give, you encrypt it, create bunch of random zeros and ones, and then you just give that message and call the decryption. Instead of encryption, you call the decryption and see whether you got your original message. It is as simple as that. Now, how many tests we have to try, whether how to guarantee your implementation is correct, that is different. Wait until I talk about verification and using Wiki proof. Any question on the usage of AES counter mode? So, you need to have a notion of this. Now, this is where I want to introduce something. Let me go back to security engine. Security engine, and this would be a problem even bigger when you do RSA. RSA key size is 1024 or 2048, it is not 128. And this security engine, when is sitting in this AXB bus, this AXB bus, these are, remember, these are standardized buses, you and I did not design it. So, the company who is selling security engine have no choice, and this bus typically has bandwidth of 32 bits. Now, for security engine to call my AES, routine, can anybody tell me? You are an engineer, tell me what are the engineering issues? By the way, we faced all these issues. So, exactly that is how we know, and our solution is used by commercial tools. What are the issues here? AES understands these stuff, that is why I wrote it down. This needs, I showed you the thing, it needs all these. This particular case we are interested. So, block in, this is 120, this is not the key size, this is the block size. For AES, irrespective of AES 128, 256, all that stuff, block size is 128 bit. So, all these are fixed, they need exactly this thing and start signal 1, and then you have to wait for the done signal, right. So, the question is, how do I transfer all these data? I, as in security engine, I got a request from CPU. How CPU transfer, that is also a little complicated, because these are all memory mapped IO. How many of you know what is memory mapped IO? So, basically for security engine, so if you are thinking that CPU or processor, if you are thinking CPU or processor is simply taking a track and putting everything in that track and sending it, it does not work that way. Even in this bus protocol, or the way the transfer happen, or this security engine, the way you want to visualize this, there is a piece of memory based on this transfer. How this happens I will not talk, I will explain the same thing on this bus. So, there are locations from certain address 000 to 111, for example, a specific byte or location has a specific meaning, maybe the first one is, and it is all hard coded. First one is key size, second one, or from then on all the bytes are the actual key, then the mode, and so on and so forth. So, therefore, security engine when it is sending the request or AES going to read, it is really not reading from security engine, it is really reading from that memory byte by byte or 4 bytes at a time. So, the question is, if you are reading 4 bytes at a time, but none of them looks like 4 bytes, this is 120, 256, it is really lot of bytes. So, how do you take care of it? Think of you are an engineer working in a company, that is exactly the problem given to you, that you are connected to a bus that can transfer 32 bits in a clock cycle, and you have to transfer all these stuff. How would you do it? Just give me some layman's view, how would you implement it?
Multiple clock cycles.
Multiple clock cycles. So, basically in the community you call it you need to write a wrapper logic. You write another function, and from that function you call this function if you are doing in software, and that wrapper logic need to have a finite state machine. That finite state machine needs to read 32 bit at a time. Just to get even just the key itself, it needs 4 cycles. So, it needs to have a finite state machine that counts 4 cycle or 4 states. Only at the beginning of 4th state, then it knows key ready. Then after nonce and all that, it is going to take time. When all of them is done, only then that finite state machine is going to do the start signal 1. Because you have to kind of understand, you are reading from this memory, it is getting 32 bits at it, and this problem is more severe for RSA. When we go, you will talk about 1024 bit key, and nobody uses 1024, 2048 bits key itself for RSA. Anything smaller than that is truly vulnerable. Any questions on this? So, when you go to industry, this is exactly what you are going to face. Your expectation would not be I write a function, I call a function, it works, it will not going to work. So, the wrapper logic is the key idea. And in fact, wrapper logic is very common in security domain. In fact, there are many security engines who actually do monitoring of different component. So, if you are following that convention, story is slightly more complicated. So, think of a CPU, your some kind of controller and all these components you have, all these controllers you have, then you have the security engine. So, one of the objective of security engine, whichever company follows that policy, is that security engine has kind of connectivity to all these places. It is not a great design principle. This is more security unfriendly than, and everybody has a wrapper logic. Anytime dynamically you want to implement certain security protocol, these protocols are getting checked here and security engine updates that. So, for example, this one checks any value coming in has to be a positive integer. Let us say that is what it is checking, negative number they do not like, but 10 days later the company policy changed and maybe the people are getting negative salary, whatever it is. So, then that policy got implemented, right. So, then this security policies and security engine checking those policy. So, the wrapper logic in highly secure environment or the design that are for safety critical system that needs protocol update, security protocol update. So, that is basically the kind of story we deal with. And many of you, those who go to different consulates, different countries consulates, they keep changing their rule. So, you really have to have a wrapper logic. You just do not rely on what your brother or parents, how they got the visa. You kind of understand, okay, what are they expecting now, how many letters, how many forms. So, that is kind of the story. When things keep changing, new, so think of antivirus running, another signature, you know, that checking whatever, when you can dynamically do that, but this has a significant performance bottleneck. Any question on this sorry, on this utilization, getting byte by byte, creating the wrapper logic and then implementing it? Yes, please.
We are using wrapper to make performance enhanced.
No, we are introducing wrapper so that two people can talk. This one talks in Bengali, this one talks in Hindi. So, you need an interpreter. Here thing is the bus we use, that is a standardized, that cannot be changed. So, that allows 32 bits per cycle. So, therefore, to transfer all these bytes, 32 bytes, you need at least 4 cycles of transfer. Somebody needs to keep track of it. Did I have the full key? Right. So, that is counter, that FSM, whatever you implement, that software, that is your wrapper or glue logic. Okay, now, the counter mode, Galois counter mode, this is basically used in your TLS protocol. So, basically just this part is new and this part is essentially in layman terms doing the authentication. And the community has a nice name for it, such kind of encryption, authenticated encryption. This is known as authenticated encryption. And if you look at observe this part, this is nothing but your same counter mode. This is exactly same counter mode, no changes. But in addition to that, it is basically generating your authentication output. In addition to your ciphertext, it is creating authentication output. It still has the same thing, it should have same thing, the start, maybe I forgot to write, it still should have start, it should have done and authentication ready and all that stuff. Any questions on, or at least the incremental part of the story? And this is basically using Galois field multiplier, and this also, because it is doing authentication, it needs a hash key. So, it is basically, think of this is an authentication. I did not talk about hashing yet, but think of this is a kind of similar to hashing.
What is happening in the authentication?
So, so exactly the way any authentication works, you basically get any object or key or anything, you map it to other way around. You get a message, you map it to a key. So, the pointer is other way. You get a message, you point to a key. It gives a unique identifier. whatever the any hashing function, whatever it does, this is lot more secure than that. Whatever SHA does, anytime you hash to a hash table, this is basically Galois field is going to create a tag for that. And instead of using one authentication, one encryption, this is authenticated encryption, you get both out of it. And the XTS I do not believe people uses, but it has all the stuff of previous one. I should be able to show somewhere. This no, it is kind of slightly modified. So, this part is there, then it makes some tweaks, and all of those pre-tweak, post-tweak, all of those are there, and you have your separate encryption and decryption. This is kind of different than previous implementation. In previous implementation, same computation is inverted. You give the ciphertext and the key, it will produce the original message. You give the message and key, it will produce the ciphertext. But here there is a separate encryption and decryption logic, and this is basically cycle stealing. So, now I am going to talk about the next one, which is elliptic curve cryptography. Let me just basically introduce this, and in the post I will talk about the remaining part. So, elliptic curve basically, as you see the name, it basically elliptic curve is a mathematical curve with lot of interesting properties, and the reason these algorithms are secure because of the elliptic curve. And the problem with before even you talk about designing it, let us talk about testing it. When you have a elliptic curve encryption algorithm, you cannot do the testing we did for the AES. You give any message, you encrypt, you do decrypt, because for you to do this elliptic curve cryptography, you have to give 2 points P and Q, and those 2 points cannot be any random point, they have to be valid point on the curve. In fact, for any people who are working many years in the cryptographic domain, it is actually very difficult, we found out painfully. So, what we do, we go to the NIST website, there are a lot of curves, the curve has its name, and there are a lot of points somebody figured out. You just do not bother about it, who figured it out, just go and take those P and Q point if you want to test whether your implementation is right. And basically lot of operations are on P and Q, and elliptic curve basically implements a function similar to this. It does a y square, x cube, and some function of x, a polynomial of this nature, and that could this value could be 0, 1, whatever it is, and that is basically the curve. That is the elliptic curve, and all the operations are on the elliptic curve, and the key idea is finding a point or finding a solution. If you know only one point or the other, you will not be able to figure out the other one, that is the idea. Now, so the elliptic, yes please.
So, what is this curve represent? What is your x axis and y axis?
So, this function, whatever function you choose. So, but the function will have these characteristics, it has to have y square, it has to have x cube, and then it has to have x to the power something, plus minus is fine, and this may or may not have this number, that is really called
Same x value we have 2 y value, right? So,
sorry, say again.
so for same x value,
In this particular example you have 2 y value, yes. So, depending on that function, what that exact function is. So, the function would be something similar to this square would be there, that is required, and this cube, this is required, and this is x to the power 1, this is required, and there could be a constant. There could be a constant value here, may not be a constant, plus minus both are fine. So, that is the function of elliptic curve for elliptic curve cryptography. That special class of function this algorithm is designed. Somebody figured out that function is ideal for this, not any other polynomial, that is the exact polynomial it has to be. So, now this was introduced in NIST 1999, and it basically uses modular exponential in Galois field. When I talk about RSA, I will zoom into it. Only difference between RSA and elliptic curve is in RSA all these numbers is for normal number, I do not know whatever the mathematical name for it, any of those integers, but here this number has to come from the curve, and that is basically the level of difficulty, and not to mention elliptic curve cryptography is also broken. that is why this post quantum cryptography, which we will talk on Friday.
So what is the plain text? What is the key? Because
So, I will come to that, I will come to that after the thing. So, elliptic curve cryptography has kind of two variations. One is the encryption one, the elliptic curve encryption scheme, and second one is signature DSA, which is authentication, sign and verify scheme. So, when I talk about the encryption scheme, we will talk about the message and key and all that stuff. Thank you, and we will talk about it after the break.